Hello friends, welcome you all to the 20th lecture on function analysis and its applications. In this lecture, we will discuss the consequences of equivalent norms with examples and on a finite dimensional space. All norms are equivalent. These are the contents, consequences of the equivalent norms with examples. On a finite dimensional space, all norms are equivalent. Isometry. Definition. Let n and n dash be two normed spaces over the field F. Then a linear transformation T such that n to n dash is said to be isometry or isometric isomorphism if it preserves the norm as follows. Norm Tx is equal to norm x for all x belonging to n. Further, if any xy belonging to n, then norm Tx minus Ty. This can be written as Tx minus y because T is linear. And as per this, we can write norm Tx minus y is equal to norm x minus y. That is for all xy belonging to n, norm Tx minus Ty equal to norm x minus y. Equivalent norms. Already we have discussed the definition and some examples of equivalent norms. In this lecture we will discuss further consequences of equivalent norms and related theorems. Corollary. First, the two norms norm 1 and norm 2 on n are equivalent if and only if the sequence xn converges with respect to norm 1 converges with respect to norm 2 and conversely. That is, two norms are equivalent if and only if convergence in norm 1 implies and is implied by convergence in norm 2. Second corollary, the two norms norm 1 and norm 2 on n are equivalent if and only if every Cauchy sequence with respect to norm 1 is also a Cauchy sequence with respect to norm 2 and vice versa. Example. First example, let n is equal to L2. Define for each x is equal to x1, x2 and so on, xn dot dot dot. That is infinite dimensional. Norm x1 defined summation I is equal to 1 to infinity mod xi square whole power 1 by 2 and norm x2 summation I is equal to 1 to infinity mod xi upon I. Okay, here two norms defined as such type. Then norm 1 and norm 2 are not equivalent. I have already given some examples of equivalent norm in earlier lecture. Okay, so here we give the examples when norms are not equivalent. Okay, so here n is equal to L2 and norm defined as such type norm x1 is equal to this one and norm x2 is equal to this, then norm 1 and norm 2 are not equivalent. Since ei under norm 1 tend to 1 as I tend to infinity and norm ei under second norm, this is tend to 0 as I tend to infinity, where ei is equal to 0, 0, 1, 0 and so on. At the ith coordinate 1 and 0 elsewhere. Okay, so norm x1 is 1 and norm x2 tend to 0 as I tend to infinity. Okay, so norm 1 and norm 2 are not equivalent. Example 2, let n equal to C01 set of all continuous linear functional under the closed interval 0 to 1. Let us define two norm as this. Norm f1 is equal to max of mod ft t belonging to closed interval 0 to 1 and norm f2 f under norm 2 defined integral 0 to 1 square of ft dt whole power 1 by 2. It is also not equivalent because C01 is complete with respect to norm 1 while it is not complete with respect to norm 2. Already we have proved the such type of norm defined with norm linear space C01. Then first one is a Banach space and second one is non-linear space but not Banach space. Okay, so first is complete and second is not complete. So norm 1 and norm 2 are not equivalent. Example third. If n is a positive integer, LPn represents the different non-linear space for different values of p. P lies between 1 to infinity. On the same set of all n tuples x1, x2 and so on xn, so that these norms on LPn are all equivalent to one another. Now, norm xp equal to summation I is equal to 1 to n mod xi power p whole power 1 by p, where p lies between 1 to infinity. Proof. Here x is equal to n tuples of x1, x2 and so on xn belonging to LPn. Let a sequence xr of x, then xr has n tuples, that is xr1, xr2 and so on xrn. Okay. Let xr converges to x, where x, x1, x2 and so on xn as r tend to infinity in the pth norm. We shall show that the convergence with respect to each norm is equivalent to coordinate-wise convergence. Norm of sequence xr minus x under the pth norm equal to summation I is equal to 1 to n mod xri minus xi power p whole power 1 by p. We can write, since xr converges to x as r tend to infinity, given epsilon greater than 0 and can find a r0 positive integer r0 such that as per the definition of convergence, norm xr minus x under pth norm defined as this summation I is equal to 1 to n mod xri minus xi power p whole power 1 by p less than epsilon for all r greater or equal to r0. So expanding this one as n terms, that is, this can be written as mod xr1 minus x1 power p plus xr2 minus x2 power p plus and so on plus xrn minus xn power p whole power 1 by p less than epsilon. Okay. So taking the pth root of both sides, we have xr1 minus x1 power p plus and so on plus xrn minus xn power p less than epsilon power p. Okay, so here we have n terms. Sum of n terms less than epsilon power p. It means each term less than epsilon power p. That is xri minus xr power p less than epsilon power p. That is taking ps root of both sides, xri minus xr less than epsilon. Okay, so this is the convergence of xri to xr in RRC, where as individual this is xi. Individual xi, that is real or complex. Okay, for fixed I. So from equation 2, xr converges to x in norm p for fixed I. Since equation 2 is independent of p, here equation 2 independent of p. So now we can take the qs power of both sides. Okay, so we have summation I is equal to 1 to n xri minus xi power q whole power 1 by q less than epsilon. Okay, so it can be obtained easily. Which properly chosen? This implies xri converges to x in norm q, where q lies between 1 to infinity. Thus, xr converges to x in norm q. Also, by interchanging p and q, we can show that xr converges to x in norm q, then xr converges to x in norm p. So, by the corollary, norm p equivalent to norm q. Since p and q are arbitrary, all norms are equivalent to one another. Hence proved. Next theorem, this is the important theorem. On a finite dimensional space, all norms are equivalent. Let n be a finite dimensional space with dimension n, and x1, x2 and so on xn be a basis for n. For any x belonging to n, there exist unique scalars alpha 1, alpha 2 and so on alpha n such that x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. This equation 1. It can be easily proved norm x0 equal to maximum of mod alpha I for all I 1 less or equal to I less or equal to n is a norm on n. So such type of norm already we have proved in earlier lectures. So it can be proved easily norm x0 equal to max of mod alpha I is a norm on n. So detailed proof we ignore here. We call this particular norm zeroth norm and so the any other norm this on n is equivalent to this norm. This amounts to finding positive constant small m and capital M such that m norm x0 less or equal to norm x less or equal to m norm x0 for every x belonging to n. The right hand side of equation 3 is easily proved. For any x belonging to n, we have from equation 1. This is equation 1. This can be written as summation I is equal to 1 to n alpha I xi. Okay. So equation 1 can be written as norm x is equal to norm of summation I is equal to 1 to n alpha I xi. This can be written as less or equal to summation I is equal to 1 to n norm alpha I xi. Alpha I is scalar, so this can be written as mod alpha I norm xi. So norm x less or equal to summation I is equal to 1 to n mod alpha I norm xi. But here alpha I norm xi. Okay, so this can be written as mod alpha 1 norm x1 plus mod alpha 2 norm x2 plus and so on. So here alpha 1, alpha 2 and others mod alpha I, that is different. So we can take max value of alpha I in each term. Okay. So this is also less or equal to max alpha I summation I is equal to n to n norm xi. Okay. So here max of mod alpha I denoted by norm x0, zeroth norm. Okay. So this is less or equal to zeroth norm x and summation I is equal to n to n norm xi. Suppose summation I is equal to 1 to n norm xi is a constant m. Okay. So here norm x less or equal to constant m and zeroth norm. So we have norm x less or equal to m norm x0. Equation 4. Okay. So this part is proved. Now we prove this part. To prove the left hand side of equation 3, this one, we proceed by induction. Now consider the case of one-dimensional space with the basis x1. Okay. Here we have the basis x1, x2 and so on xn. Then any vector of this one-dimensional space is uniquely written as x is equal to alpha 1 x1. Okay. Why? Because here we have n-dimensional basis x1, x2 and so on xn. So vector x is equal to x1, x2 and so on xn. It can be written as x is equal to alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. So here one dimensional basis, that is only x1. So we can write x is equal to alpha 1 x1. Okay. So for basis x1 uniquely written as x is equal to alpha 1 x1. Hence norm x is equal to norm of alpha 1 x1. Alpha 1 as scalar, that is mod alpha 1 norm x1. Here only one term, that is mod alpha 1 as norm x0. So mod alpha 1 norm x1 can be written as norm x0 into norm x1. Thus in the one-dimensional case, the positive constant m on the left hand side of equation 3 can be taken as norm x1. This is the equality case of this. Now suppose the theorem is true for all spaces of dimension less than or equal to n minus 1. Let L is equal to x1, x2 and so on xn minus 1 be the subspace spanned by the first n minus 1 basis vector. Then by induction hypothesis, norm equivalent to zeroth norm on L. Next, we show that L is closed subspace of N. For this, it is enough if we show that L is complete. So to prove the closed subspace, let YR be a Cauchy sequence in L. Okay, so this Cauchy sequence converge in same space, that is closed. So let us check. Let YR be a Cauchy sequence in L with respect to the norm this, since norm this equivalent to zeroth norm. It follows that YR is a Cauchy sequence with respect to zero norm also. Let sequence YI can be expressed alpha I1 x1 plus alpha I2 x2 plus and so on alpha IN minus 1 xn minus 1, where alpha I1, alpha I2 and so on alpha IN minus 1 are uniquely determined scalars with respect to the basis x1, x2 and so on xn minus 1. Since YR is a Cauchy sequence, we get norm YR minus YS under 0 norm tend to 0 and RS tend to infinity. Okay, as per the definition of Cauchy sequence. But norm YR minus YS under 0 norm equal to max of modulus alpha RK minus alpha SK tend to 0 and RS tend to infinity, because norm X under 0 norm equal to max of mod alpha I. Okay, so we can write here norm YR minus YS under 0 norm equal to max K mod alpha RK minus alpha SK tend to 0 as RS tend to infinity. Hence equation 5 implies mod alpha RK minus alpha SK tend to 0 as RS tend to infinity for each K 1, 2 and so on n minus 1. Okay, here max value tend to 0, it means any modulus value tend to 0. Equation 6. Equation 6 is a Cauchy sequence over RRC. Here this one as individual scalars, so that the Cauchy sequence over RRC. Hence equation 6 Cauchy sequence over RRC, which is complete. Hence alpha RK converge to alpha K as R tend to infinity for each K is equal to 1, 2 and so on n minus 1. Let Y is equal to summation K is equal to 1 to n minus 1 alpha K xk. Then Y belonging to L and YR converges to Y with respect to 0 norm, because here YR converges to Y and alpha RK converges to alpha K with respect to 0 norm. Since norm 0 equivalent to norm on L, it follows that YR converges to Y with respect to norm 0. This implies that YR converges to Y with respect to norm. Thus, under the induction hypothesis, we have proved the subspace L is complete with respect to the arbitrary norm, and so it is closed. Moreover, from the above we see that this statement will be true for any finite dimensional subspace of normed linear space. Now, if Xn be the nth basis vector, consider the set xn plus L equal to xn plus z such that z belonging to L, and also the mapping z converges to xn plus z from L to xn plus L. Okay, z is the element of L and xn plus z from L to xn plus L. Okay, this is the mapping. Also let y z belonging to L, then we have norm xn plus z minus xn plus y can be written as norm z minus y. This shows that the mapping z to xn plus z is isometric. Okay. We know that the condition for isometric, if t such that x to y, then norm of tx equal to norm of x for all x belonging to x. So here mapping from L to xn plus L. Okay. So norm of this equal to norm this one. Okay. So this shows that the mapping z to xn plus z is isometric. Hence, since L is closed, the space xn plus L is also closed. So its complement xn plus L C is open. This is the notation of complement. So complement of xn plus L is open. We also assert that 0 is not an element of xn plus L. For if 0 is the element of xn plus L, then for some scalars beta 1, beta 2 and so on beta n minus 1, then 0 is equal to, as per this definition, we can write xn plus the vector beta 1 x1 plus beta 2 x2 plus and so on beta n minus 1 xn minus 1. So 0 can be expressed as xn plus beta 1 x1 plus beta 2 x2 plus and so on beta n minus 1 xn minus 1, which is impossible since xn not equal to 0. This proves that 0 is not an element of xn plus L, because here 0 is this one, so xn is equal to minus of this. Okay, so this proves that 0 is not an element of xn plus L. Since complement of xn plus L is open, there must exist a constant Cn greater than 0 such that the open sphere S0 Cn, that is 0 is the center and Cn is the radius of the open sphere. It is defined by x such that norm x less than Cn. Okay, because this is the open sphere, is wholly contained in complement of xn plus L. This implies that over any x belonging to xn plus L, we have norm x greater than Cn. Okay. This is for complement of xn plus L. So this implies that for x belonging to xn plus L, that is reverse of this, we have norm x greater or equal to Cn. Thus for scalar alpha I, norm alpha 1 x1 plus alpha 2 x2 plus and so on alpha n minus 1 xn minus 1 plus xn greater or equal to Cn. If alpha n not equal to 0, we replace alpha 1 by alpha 1 upon alpha n, alpha 2 by alpha n, and so on. So we have norm alpha 1 upon alpha 1 x1 plus alpha 2 upon alpha n x2 plus and so on alpha n minus 1 upon alpha n xn minus 1 plus xn greater or equal to cn. So solving this, okay, we have norm alpha 1 x1 plus alpha 2 x2 plus and so on alpha n minus 1 xn minus 1 plus alpha n xn greater or equal to mod alpha n cn. Okay, by taking the LCM alpha n and cross multiplication, we have this. Here we notice that instead of starting with space L spanned by x1, x2 and so on xn minus 1, we can start with the space spanned by x1, x2 and so on xn. In a similar manner, we can find some positive constant Ci such that norm alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn greater or equal to Ci modulus of alpha I for any I equal to 1 to n. We can assert that for any x is equal to summation I is equal to 1 to n alpha I xi equal to norm alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn. Okay, greater or equal to minimum of Ci into mod alpha I. So here Ci we have taken minimum value of Ci for any I is equal to 1 to and so on n. Since equation 8 is true for each alpha I, it is true for the max value of alpha 1, alpha 2 and so on alpha n also. So we get norm alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn greater or equal to minimum value of Ci into maximum value of alpha I. And we have max value of alpha I, that is norm x0. Okay, hence we get norm alpha 1 x1 plus alpha 2 x2 and so on plus alpha n xn greater or equal to minimum Ci into norm x0. Taking m is equal to minimum of Ci, small m. Okay, then we have from the above inequality, we have norm alpha 1 x1 plus alpha 2 x2 plus and so on alpha n xn greater or equal to m norm x0. Okay, so left hand side of equation 3 is proved here. So from equation 4 and 9 we get m norm x0 less or equal to norm x less or equal to m norm x0. This completes the proof of theorem. Okay, here equation 3 is this one. Okay, so left hand side of equation 3 also proved, and here in equation 4 norm x less or equal to m norm x0, and from equation 9 this is norm x, this is greater or equal to m norm x0, that is m norm x0 less or equal to norm x, which is from equation 4 less or equal to m norm x0. This completes the proof of the theorem. In this lecture, we discussed the consequences of equivalent norms with the examples, and on a finite dimensional space, all norms are equivalent. These are the references which have been used in this lecture. Function analysis, Dover publications by George Beckman and Lawrence Narsey. Introductory Function Analysis with Applications, John Valley and Sons, written by Erwin Krejcik. Function Analysis, New Age International Publisher by B.V. Lemieux. And Function Analysis, Tata McGraw-Hill, written by Waterloo. Thank you.